So let's continue our series on Physical Principles 1. Uh, so previously we stopped here, no? The ideal gas law, pressure, volume, the units of volume. Ideally, it's important that you memorize them, but it still depends on your professor. We also have temperature, the conversions. Although, personally, I think that um, the calculator that you have has a conversion um, between Fahrenheit and Celsius. So I think what you have to worry about left is the conversion from Celsius to Kelvin and vice versa, and conversion from Fahrenheit to Rankine and vice versa. So yeah, it's basically it. For this part, the amount of substance, this is represented as N. This is the amount of substance that contains as many elementary entities as there are atoms in 12 grams of AC12 isotope. That's the formal definition. Um, Although simply, you can just call this as um, having these units. No? You have grams per mole, grams per g-mole, kilograms per kilomole, pounds per pound mole, etc. So, although these are the main units that they use. Um, so the amount of substance in a mole is related to the mass by the molecular weight over molar mass rather, of the substance. So the mole is equal to the mass of the substance. This is expressed in grams, typically, divided by the molar weight or molar mass. Um, it's essentially the same idea. It's actually shown here. For atoms, we call it atomic weight. For molecules, we call it molecular weight. For ionic compound, this is the mixture no, of a metal and non-metal. We call it formula weight. So essentially, the more generalized term is molar mass. So yeah, we have the universal gas constant. This is named after Victor Regnault. This is represented as R, capital R. In other words, called the molar gas constant or the ideal gas constant. So this is the molar equivalent no, to the Boltzmann constant, represented as K sub D. So at least for the Canon F789 SGA1, the constant number for the Boltzmann constant is 25. And for Avogadro's constant, that's 24. So you don't have to memorize the numbers, no? At least be familiar with it only. So essentially, the universal gas constant, R, is equal to K sub B times N sub A. So you just multiply the Boltzmann and the Avogadros. So we have the following values for R. As mentioned, it is a constant. So these are the values with the different kinds of units that you will encounter. So the most common ones you will encounter are this one, 0.08 to 0.6 liter atmosphere per mole Kelvin. We also have 8.314 joules per mole Kelvin. Um, if it's in AES units or American Engineering System, then 10.73. In other words, English units. We also have 1.987 calories per mole Kelvin. Eventually, by the time you reach around long quiz 4, you'll have this a little more often. Or at least LQ3, long quiz 3, 1.987. You will see or encounter calories. 1 calorie is 4.184 joules. Yeah, I think that sounds about right. Um, the least you'll encounter most likely are 1545.35 foot cube pound force per pound mole Rankine and 1.98588 BTU per pound mole Rankine. So ideally you have to memorize everything. You may not need everything in this subject, but in future courses, it might be important that you are knowledgeable of these numbers. Otherwise, you might not be able to solve a problem because they're already expecting that you have already memorized these. No? So make sure you comply with step 1. Okay, so standard conditions, we have uh, STP, NTP, and SATP. So for standard, the temperature is 0 degrees Celsius, pressure is 1 atmosphere. Actually, for the corresponding molar volumes, you can calculate them. Uh, so molar volume is basically just the volume divided by the mole. So this is, if we bring out our ideal gas equation, PV equals nRT. So if you transpose n to the left side, so V and n are expressed in such a way that they are divided, no? V over n. Then what you have at the right side is RT over P. So in other words, molar volume V over n is equal to RT over P. R, um, let's express R as 0.08 and temperature as we have to convert this to Kelvin. So 0 degrees Celsius to Kelvin is 273.15. No? So 0.08206 times 273.15 divide by the pressure of 1 atmosphere, no need to convert. No? Because your universal gas constant is, it has the unit atmosphere and Kelvin. So it was only the temperature that we needed to convert to Kelvin. So yeah, divided by 1, then you get the molar volume 22.414. That is for standard temperature pressure. So the logic is the same, no? For NTP and SATP. You just substitute with the appropriate corresponding temperature and pressure values. So for normal temperature pressure, 20 degrees Celsius, in other words, to 93.15 Kelvin. And still 1 atmosphere for the pressure. And for SATP, this is the temperature is 298.15 Kelvin or 25 degrees Celsius. For common temperatures expressed in Celsius, such as these, it's beneficial if you already know its Kelvin conversion, no? Without calculating. It's pretty simple. 273 plus 20, 293. 273 plus 25, 298. Then don't forget the point 15 to be more accurate, practically. So we have standard ambient. Um, sorry, uh, I'm referring to this rather. 1 bar is equal to 100,000 pascals. This is, in other words, equal to 0.986923 atmosphere. It's also beneficial to memorize this. 1 atmosphere is 101,325 pascals. This is also 1.01325 bar. So, yeah. What else? Okay, so we have other ideal gas laws. We have the Boyle's law. Boyle's law VP. So we hold temperature as constant. In other words, this process is isothermal. And we have a fixed amount of an ideal gas. So from PV equals nRT equals constant, it becomes PV P1 V1 equal to P1 V2. So we have initial and final states. For Charles' law, this is Charles V over T. No? So we consider this as an isobaric process because of pressure being constant, being held constant here. So yeah, again we have initial and final states, sub 1 and sub 2. For Gay-Lussac's law, this is pressure over temperature of initial equal to pressure over temperature of the final. And in this process, since we don't see volume here, volume is constant. And so we call this process as isochoric. For Avogadro's law, we have, it's basically the molar volume, no? V over N. So V sub 1 over N sub 1 equals V sub 2 over N sub 2. Now we have the combined gas law. So it basically shows the relationship of PVT for the fixed mass or quantity of the gas. So coming from PV equals nRT, we transpose T to the left side, no? So it becomes PV over T equals nR. And so P1 V1 over T1 equal to, no. I pronounced that correctly. I stand corrected. P2 V2 over T2. Okay? So, yeah, for a fixed amount of or mass of gas in a mole, the ideal equation, a gas equation becomes this. No? Okay. Dalton's law of partial pressure. For the mixture of ideal gases, the total pressure of the mixture is equal to the sum of the individual partial pressures of the gas components at constant volume. No? So the process is isochoric. Also, constant temperature, so the process is also isothermal. So simply, N1 plus N2 equals Nt. And for an ideal gas, V sub 1 equals V sub 2 equals V sub T. So basically the volumes are the same, no? As well as the just the volumes rather. For the pressures, we add them. This one, what you see in red, that's gonna be useful. Uh, it's actually performed, no, or used in chemical engineering calculations or CHICALC. Partial, the partial pressure over total pressure gives you the mole fraction. So yeah, partial pressure of an ideal in a mixture is then related to the mole fraction as the following. Okay. So yeah, the P becomes N in the context of what's written here. And yes, we are under the assumption that the pressure of a gas is partial pressure if it alone is present in a container. There shouldn't be any other gases here. So yeah, thus the partial pressure of an ideal gas in a mixture is given by this one. So if you transpose the total pressure to the left side, then you get P sub I equals Y sub I times P sub T. So yeah, this is the one you see here. You just see the summation. It's quite a lot, no, of literature. Okay. So after Dalton's law, we have Amagat's law. This one is for partial volume. Same concept, N1 plus N2 equals Nt. In this process, we consider it as isobaric, so constant pressure, and isothermal, so constant temperature. Uh, so you have all that. The Loschmidt constant, N sub O, is the number of particles of an ideal gas in a given volume at standard temperature pressure. This is featured, obviously, in physical principles, although it hasn't really been a big topic in comparison to the other lessons. No, so we'll leave it at that. Honestly, I did have a question on this, and I think it's still unresolved to this day. So It's better that I don't teach something that I don't understand fully. So we'll leave it at that. Let's go to Graham's law of effusion. So the rate of effusion, um, actually there's a difference, no, between effusion and diffusion, but there are some cases where they're basically the same idea. No, it just depends on the context. In this case, they're synonymous. So the rate of whether it's effusion or diffusion of an ideal gas is basically inversely proportional to the square root of the molar mass of the gas. So how do you express that in an equation? So it's this one. So inversely proportional, you see r sub 1 over r sub 2 equals m being capital M being the molar mass. No, sometimes I write it as double M capital or single M capital. So um, in my videos, I will be interchanging them. No, but they're essentially the same thing. That's my terminology. Okay, so capital M sub 2 over capital M sub 1. Don't forget the square root. So in the same sense, the molar mass could be expressed as the amount of gas transferred over the time of effusion of gas 1. So you can say that um, how do we transform this algebraically? The time of infusion of gas 2 that goes to the numerator, and time of infusion for gas 1 goes to the denominator. So essentially, how you understand this formula is, we have R1 over R2, M2 over M1. Here, T2 over T1, M2 over M1. You see, the number 1 and 2, 2 and 1, that is for R and M. Here, T and M. Uh, if you have sub 2 in the numerator, it's also sub 2 in the numerator of the molar mass. So notice that difference. That certainly isn't the best explanation, but yeah, it's basically how I'd explain it for now. Effusion versus diffusion. So this is where they are different. Effusion occurs when gas molecules escape through a pinhole. So, for example, perfume. So there's a pinhole, no? You spray. So as simple as that. For diffusion, that is what happens after spraying. This is when one gas mixes with another by thermal random motion. That's when the amount that you sprayed spreads through the air, no? So yeah, let's go back to effusion. This is the ability of a gas to travel through a small opening. So that could be in the form of a pinhole, and it occurs when the aperture is smaller than the mean free path. And yes, it occurs due to difference in pressures. Because again, you are spraying, so there's obviously a difference in pressures. For diffusion, this is the ability of gases to mix in the absence of a barrier. And it occurs when there are no holes or if holes are larger than the mean free path. We'll encounter this in long quiz 2, mean free path. And yes, this occurs due to a difference in concentrations. This is the driving force. So, what do I mean by difference in concentrations? When you spray perfume in a room, before spraying, it normally doesn't smell. No, the concentration of the air is without the perfume, but after spraying, that's when you feel a difference in concentration. Uh, I think I described it the other way around. So after you spray, um, that is because of a difference in concentrations. That definitely isn't the best explanation, but most importantly, you know the difference between what they are. So one is pinhole, that's a keyword for effusion, For diffusion, that's thermal random motion. Okay. Okay, so we are definitely going to discuss this part in the next video. Bye bye. I'll make it part 3.